Steinhauer here, welcome back. Continuing our discussion of galaxy morphologies and the differences between the different types of galaxies. Moving on now to elliptical galaxies. And elliptical galaxies are so called because, well, they look elliptical in shape. And elliptical galaxies don't seem to have any kind of disk component at all. They are purely halo objects. They don't even seem to have a bulge, really. They are simply a mass of halo stars with no preferred direction of rotation, with no preferred circular versus elliptical orbits, with no preferred plane in which any of these stars rotate. They are a spherical mass of random motion of stars through them. And you can see the color of this galaxy looks much different than the color of in a spiral galaxy. This is all reddish yellow. There are no star forming regions. There's no blue stars. There's no dust lanes. There's no active star formation going on in these galaxies at all. All star formation has ceased. These are all an older population of stars in these galaxies, which is why they look red. Here are some pictures of elliptical galaxies. They're not nearly as photogenic as their spiral galaxy twins because, well, there's no interesting things going on in them. They're just a huge mass of old stars. But you can see some of them are fairly circular and some of them actually can get quite elongated. The one on the right especially seems to have an elongation along a particular axis. Some of them are purely circular, though, to look at. Here's another couple of pictures of elliptical galaxies. No, of course, not the big one. This is the Andromeda galaxy, but Andromeda has two satellite galaxies, which are here and here. And those two galaxies are, in fact, elliptical galaxies. In fact, they're dwarf elliptical galaxies. And elliptical galaxies have the unusual property that they can be among the most largest galaxies in the universe and also among the smallest galaxies in the universe. There's a huge range in the sizes of elliptical galaxies. Spiral galaxies vary a little bit, but a factor of 3 to 4 between the biggest ones and the smallest ones. There are many orders of magnitude in difference in size between the smallest elliptical galaxies and the largest elliptical galaxies. Now, there's even a type of galaxy that's kind of in between spiral and elliptical galaxies. These are called the lenticular galaxies. It's a pretty sparse group. There aren't a lot of these galaxies out there, but they're worth mentioning because it's kind of an intermediary step between an elliptical and a spiral galaxy. And this is a galaxy that has a disk component like a spiral galaxy, but doesn't have the spiral arms and doesn't have the active star formation and doesn't have the spiral arms of a spiral galaxy. So it's kind of an intermediate between a spiral and elliptical galaxies, the lenticular galaxies. Here's a couple of examples of lenticulars. There just aren't that many of them out there, but it is you'll see them listed in some things coming up. So I wanted to mention them here. Okay, the final grouping of galaxies is the grab bag that contains every other galaxy that doesn't fit into one of the categories we've already mentioned, and that is irregular galaxies. And this is an example of the Large Magellanic Cloud. This is a satellite galaxy to the Milky Way, and it looks kind of like an elliptical galaxy, right? It doesn't have a disk component. It doesn't have any sort of spiral arms, but what it does have is a lot of other stuff going on. This is a galaxy where there is still a lot of nebulas. There's still a lot of star formation going on. There's still a lot of blue colored stars, very young stars. And so this doesn't fit the traditional elliptical galaxy mold. And so we call it an irregular galaxy instead. But there's no limit to how weird these things can be. Here's some more pictures of irregular galaxies. And you can see anything from the lower left, where kind of like the Large Magellanic Cloud, except much further away and much more boxy. And to this thing where who knows what's going on, to these two on top where there's clearly some merging effects going on. And this is typically what happens with many irregular galaxies. If you take two spiral galaxies and collide them into each other and begin to merge them together, you'll get some things that don't classify as spiral galaxies anymore, but aren't anything else either. And these galaxies that are in the midst of colliding fall into the irregular galaxy category. That's probably what's happening here too. You've got one galaxy smashing into another one kind of head on, and you get these tidal tails flung out. We'll see some videos later in the class where we see these animations of this happening over billions of years as these galaxies merge and combine and collide together. There was a guy by the name of Edwin Hubble who was trying to understand how galaxies evolve, and he decided to break these classification schemes up into a diagram. Often it's helpful when you're trying to understand how things evolve to classify things, to just play stamp collector and to try to morphologically make sense of the things that you're seeing. And he decided that the best way to do that was with a tuning fork diagram. And this is the famous Hubble tuning fork diagram. And what you see is that the elliptical galaxies form the neck of that tuning fork. Here you have the elliptical galaxies on the left, and he even broke them down, E0 to E5, and E7 even, based on how elliptical they appeared, right? The E0s are very circular, in fact, completely circular, and the E1s, E2s, E3s, all the way out to E7s or so are increasingly elongated, increasingly cigar-like. And so you see that evolution here. The spiral galaxies form the arms of the tuning fork, and both the galaxies that have bars on the bottom and the galaxies that don't have bars on the top. And we even have broken them up now into the SA through SB through SC galaxies, the SA galaxies being those spiral galaxies that have the tightest spiral arms and the largest central bulges, the SC galaxies being the least tightly wound and the smallest central bulges. And the same is true of the barred spiral galaxies. Large bulges here and tightly wound spiral arms for SBA, and loosely bound spiral arms and very small central bulges for the SBC. This is confusing because capital B stands for bar, but lowercase b can stand for the middle of one of these classifications. So you have to be specific and careful about how you actually talk about these galaxies. Hubble himself envisioned this as an evolutionary diagram. Hubble's idea for how galaxies evolve is galaxies start here at an E0 with a very large cloud of gas. That gas eventually settles down into a disk and it becomes more and more elongated. You eventually get the lenticular galaxies, which are, again, the intermediaries between the ellipticals and the spirals. And then you start off with a very tightly wound spiral arms in your spiral galaxy. And then as the galaxy evolves, those spiral arms unwind, and you eventually end up here in an irregular galaxy, either taking the path of a barred spiral or taking the path of a non-barred spiral. Can you think of a reason why this would be wrong from what we've already discovered and already learned about galaxies? Can you think of a problem with this particular view of galactic evolution? Think about it for a minute. Okay, hopefully you came up with the fact that, hey, which of these galaxies have active star formation and which of these don't have active star formation? The active star formation is all happening in these spiral galaxies. So it can't really be the case that these are the older galaxies and these are the younger galaxies. So this is not, in fact, an evolutionary diagram at all, but it is a useful tool still to categorize the morphologies of galaxies and place them into categories. In fact, it's more likely that spiral galaxies like these will turn into elliptical galaxies, because when two spiral galaxies collide, they begin to lose their disk-like structure and become more randomized, and also go through a period of starburst where all of the gas and the dust is turned into stars fairly quickly. So we'll talk about that in more detail later on. Okay, some other differences between spiral galaxies and elliptical galaxies is that in spiral galaxies tend to be found more in regions where there aren't a lot of other galaxies. So spiral galaxies are common in groups of galaxies where you have a few, up to a few dozen galaxies. And the Milky Way is in such a group called the local group that contains the Milky Way and the Andromeda Galaxy and one other spiral galaxy, M33. Whereas elliptical galaxies are much more prominent in huge clusters of galaxies, where you have hundreds of galaxies to thousands of galaxies. Here's such a cluster of galaxies. And you can see most of these are elliptical galaxies. And most of them are quite large compared to even the spiral galaxies that are in this particular field. And this is probably because when spiral galaxies are closer together, they tend to merge more often, and those merged spiral galaxies tend to turn into elliptical galaxies. So in regions of the universe where there are larger density of galaxies, these mergers are more common, and you're more likely to turn your were originally spiral galaxies into elliptical galaxies in the end. Okay, we'll come back in the next video and start to talk about how we can measure distances to galaxies and how we can use those distances to say important and interesting things about the universe itself. See you then.